Hello and welcome back to another episode of getting into GiG-08. There was hacker news, which also gets loaded automatically if I press my shortcut to start the video. Okay, of course. Excuses. Yeah, welcome back, Sydney.
Thanks for having me.
And today is a bit of a special episode because I don't think I can continue on that stats program just yet, which of course is still waiting for improvements, and we will improve that for sure. But I'm currently super busy with adding multi-pack index support everywhere it matters, and I'm happy to show you around, the new things that you have missed in GiG-08. And I hope it's more or less interesting. So if there's anything, ask questions right away. Just shoot. Yeah.
Sure, will do.
Multi-pack indices. Let's start with what it actually is. I think here I've got an example, a pretty good example even. So this is just some Git repository, and if you go to the pack folder, we see a lot of packs. A lot, like 200 pack and indices, so like nearly 400 files. And this is something that happens, or that is done by libgit2. So if you use git2 and you fetch some objects, it always, the pack that it receives, it's just a small thing like this one. But instead of exploding it into loose objects, it just keeps the pack itself. So you have these tiny packs that don't make too much sense. I mean, you don't really want that. It's okay to use it, but it has many disadvantages to have these small packs. It's not really what you want for performance. Loose objects is probably better in this case, but Git2 is doing this. What can you do? So GiG-08 is gonna, once GiG-08 is actually fetching things, it's gonna be a bit, it probably does that differently, but for now, this is what can happen. So there is a thing that can help in these cases, even though you never want these small packs, just saying. But when you have multiple packs, in order to speed up performance even more, you can have the so-called multi-pack index. And whereas one data, these pack files, they contain data, and these index files, they're the index for the corresponding pack of the same hash. And the multi-pack index is mapping from one index file to multiple packs. So it's like multiple indices in one. And this has the advantage that you basically have one pack that contains all the objects, or most of the objects anyway, in all the pack files that are present in the directory. And it's like an add-on, right? So data is duplicated here. These indices, they will always be there. So you can delete the multi-pack index and it will still, the repository will still work just fine. It's really just a kind of a cache, a speed up. And something that, when you do things like this, let's see, TIG all. Can I do this here? Yes. So if I take just a part of a hash here, like a short hash, Git is still able to find that one. See that? And this magic is actually working by making a prefix search. But in order to make a prefix search and know that that there is no ambiguity, you have to search all the packs and all the indices for that matter. So if you have hundreds of them, these abbreviation searches, they are really, I mean, they're worst case performance essentially. You have to go through all packs. However, through all indices, but with this multi-pack index, you just have one convenient index where you can, really quickly see if this is a unique abbreviation or not. And this is also a reason why you want these multi-pack indices, even though I'd say only users do that kind of thing. Like accessing by a short hash is something that is not done programmatically at all, ever. So not really that much of an argument, I guess, but it's a benefit that comes with multi-pack indices. usually these things are created on the server because of their improved performance, and probably there's a ton of stuff I'm missing here when it comes to the arguments for it. I think it's also conveniently mentioned here what multipack indices are and why they are so great. There's a bunch of technical documents for that. Yeah, but that's now being created. Any questions so far? Or implemented?
I mean, maybe then, yeah, exactly for what you would use these things specifically, but it's like you said, it's like a performance optimization, right? For looking up indices and packs and stuff like that, right?
Yes.
Just in the middle layer.
Yes. It's for performance, for sure. And GiG-08 should start reading these. And for that, you have to implement this file format here, which is really clean for Git's, for Git files. All right, Git kind of doesn't have the cleanest file formats usually, but this one is one of the more recent ones. And I think what's particularly interesting about it is that that is a chunk file format. So in order to make these files extensible without needing new versions or some sort of extensions like you need for these pack indices, these index files, they already have version 1 and version 2 because they have no way of being extended. And then they kind of hacked version 2 into version 1. So because version 1 was not extendable at all, there isn't even a version field in there. So they kind of have to guess whether it's version 1 or 2 based on some bytes to define a particular spot or not, and so on. So they improved on this. They learned their lesson. And now multi-pack indices are naturally extendable, and this is version 1 as well. Something that's interesting too is that this stores the kind of hash that is used in the Git repository. So there's this hash version now for the upcoming SHA-256, and who knows, upgrading to a new hash I think is going to happen regularly, so we should probably do this comfortably, right? And this file format now has the ability to do that, and that's definitely great. And for the chunks, there is just some documentation on how to read the chunk index. So there's a small part in the file that tells you which chunks they are and where they are in the file themselves. So each chunk is really just a section in that file associated with some ID. The ID is like the kind of chunk, and there may only be one chunk of a kind in that index. So chunk kind A, B, C, there's only going to be one of each in your file. So that's chunks for you. Really, it's just that. And the chunks themselves, the kind of chunk that is in that file, that's very specific to the file itself. So they always have these 4 bytes chunk ID, which is usually just something you can easily read in ASCII, which seems like a good idea. Makes it a bit easier to interact with them. And here we see that this multipack index file just has a bunch of chunks, and most of them are kind of shared with the previous standard index file. So they're really, really similar when it comes to that. But this one uses the chunk file format, and the previous index format doesn't do that. And that's the index format in a nutshell. Something I noticed when first implementing this reading of the multipack index is that it seems, this chunk thing, I've seen that before. Like, it's not entirely new to me. And the reason for that is that the chunk file format is shared across 2 file types already. So the kind of new files that Git is writing, if they're a bit more complex, or new file types that Git is making up, so to say, they're usually using the chunk file format, and GiG-08 already knows the chunk file format, which is the commit graph. So these commit graph files, oh, where is it here? These commit graph files, here, they are actually also chunk based. So commit graph is also kind of a cache to be able to more quickly read the commit graph and know, which parents are where. That's great. And that is all stored in a chunk-based file. And this is code that was entirely contributed. And I was looking at it and thought, okay, how are chunks handled here? And I saw that basically it's all just implemented by hand. So here, get the chunk ID and then get the chunk offset. So this kind of decoding is done by just getting some bytes out of a memory map data file, and then you do your thing, because the chunk file format itself is really simple. Chunk ID, 4 bytes, followed by the chunk offset. So where does the chunk start? 8 bytes, 64 bits, so can be huge files. And then the next chunk's offset is naturally the end of the previous chunk. So this gives you the size. And this is why that chunk index here, I call it chunk index. It's like a table of contents for chunks, is where C is the amount of chunks. The index has C plus 1 times 12 bytes as a size. And this plus 1 is just some sort of final sentinel chunk. So that's the last chunk in the table of contents, which has a special chunk ID, which is 0. And this just tells you this is the end of the table of contents. So this is how you can scan through, if you want to, scan through the table of contents and just figure out how many chunks there are and stop at the 0 chunk ID, whose offset is also the end of the previous chunk. And this is why that is also important to have. Otherwise, you wouldn't know how big the last chunk is, the last actual chunk, right? This is why the C+1 comes into play. Something that Git does a lot, that the last of something, whether it's real or made up, is kind of giving you the total size of something. It's something I know from these indices as well. Yeah, that's the chunk index. And here you see that all this parsing is done by hand. All the error handling is in line. I mean, it's really just, the good kind of code, the kind of stupid code that just goes through things one by one. There's a lot of offset calculations here, which, easily go wrong, I think, if you just do it like this all the time. I don't do that, by the way. I don't write code like this anymore just because I get it wrong too much. But what this code also does is once it finds a chunk, it then matches, because these can have any order, it then matches on that chunk ID to figure out what kind of thing it is. Then it does some validation. If it passes the validation, it stores the offset to the beginning of that chunk for later, so that it can actually access that data that is stored there. And this is how these formats usually work. You use the table of contents to get the chunks, do some validation, and if passed, you keep it for later for actual data access. And you see here, it implements five different kind of chunk types, and it's all kind of in line, and there's a lot of error handling here, of course. Nicely done. And that's that. This is if you do it by hand. So the chunks already existed, but now obviously I was facing the question, should I do the same thing for the multi-pack index parsing or not? So I decided not to do the same thing, but instead abstract the chunk related stuff into its own crate, So now there's git chunk as a crate that just has the few things that are needed to for now read, and in future probably also write these chunks, which is all kind of trivial, but then at least you have a nice API to handle this. This is why, and you can already share it among the crates. Right now only one crate uses it.
So that could also replace the commit graph version essentially at some point.
Yes. At some point, actually, I want to do it right away. I was working on this just now, because the git chunk crate has no actual tests right now. So the only test it gets is through multi-index test and through commit graph test. So I wanted to, see how well it applies to the kind of coding style that is used in commit graph. And I also want to make sure that, of course, it really, really works. So for now, the multi-pack index already works with that. It seems fine, but I want it to be used everywhere right away. So it's nice to have this kind of abstraction, and it was nice kind of putting this together, because it's really mostly abstraction, less actual, I don't know how you want to call it, less actual computer science. It's really just how can you make it into a nice API, because there's not so much it actually does. But it's nice to, see these differences here, because it's, commit graph. Why do I not find this commit graph init file in it here? It's nice to compare this a bit, like how the parsing is done, because I think this can tell us different styles of parsing, or teach us about different styles of manual parsing, by the way, in Rust as well. So not too uninteresting, I think. So this is commit graph. And the style employed here is always doing some offset, and the offset is like the cursor into the file. And then you see this pattern a lot, where you say offset and then offset plus some length, and that gives you some sort of segment that you can then check or use. And then you increment the offset by the thing you just saw and continue. And that's fine. That definitely works, but you have to do these offset calculations a lot, and you better don't forget to use the right offset and so on. This is really good for checking individual bytes, obviously, because now you can just do this. Just give me the byte here and you're done. But also, it's kind of problematic. I mean, not problematic, but it's error prone. I don't like to do that for that reason. I'm not good enough for that. In C++, by the way, or in C, you would not usually see this, but rather you would do this, right? So it's the post increment, and then you kind of do all this in one, and I think that's then at least you can't so easily forget, I guess, to increment the offset. So I don't know.
A little bit more woven in and hidden away, but
yeah, it's a bit more hidden, true. But the old legacy me says, if I have to use an offset, I would probably use it like this. But Rust doesn't have this, because that operator is evil. So you have to do this. Okay, fine. And this follows, or this continues here until we do this a lot, right? Where we have these individual parts and pieces. And do you remember the better way to write this? Like the more convenient way? Like this exact thing, when you see this, you can replace it with that.
Oh, okay, yes. Now I see it, of course.
Yeah.
You're essentially just taking a slice of that length. Okay.
Yes. And that's how you get rid of the math. And you make it, I mean, the direct math, right? This kind of makes it so much easier to look at, and it's fascinating that this works. But sure, this returns a slice, and from that you get another slice, and just take 4 of this, and then, Rust does the math for you. That's great. And I think that's better. If you have to do it like this, that's definitely better. And there would be no other way for me if I have to do this. Okay, let's look at let's compare with the multi-index way of parsing things, because it has to do the same thing. And let's see how it does it. Okay. So first of all, it does a header as a minimal size check to something that it usually inherits from the C code. I mean, I look at the Git code, right, just to be sure I don't miss anything fundamental. And they usually do this minimal size check to be sure they don't overshoot, because sometimes the C code, it just accesses data that might not actually be present if you don't do your boundary checks. And this is part of the boundary check. So to say, even though in in Rust, there's no issue with that because you always have boundary checks. So still, it's here kind of for completeness. When I was implementing this, I also saw, let's compare this with the hey, font size. Zoom in, zoom in, zoom in, zoom in, zoom in, zoom in. And here in the C version of that, where's the min? Yeah, they have signature. They checked that before here. Here, look at that. The MIDX min size. So they have the header size, which is 12, plus the hash algo raw size. So that's the amount of, that's all global stuff here, right? Like, where's this coming from? Yeah, it's global. It's the reason why. Yeah, anyway, multi-threading. So this is usually 20 bytes, but depending on how this is built or configured, I don't know, it's maybe more because it's a new hash algorithm. So it's kind of, this is a compile time method as well, but this is a runtime here. So this define it's resolved at compile time, but this is then part of the runtime because this is a global coming from somewhere here. And this is a global, so it needs a loaded repository to work, and it's kind of all very, you know, better don't access that before you have the repository set up somehow. So I'm just saying, it's all kind of so dangerous what is kind of common here. It's crazy. But the header size, it's basically 12 plus 20 in most cases. And the minimal header size. But remember, we have this chunk size here. So its amount of chunks plus 1. So even if C is 0, you always have one chunk, which is the sentinel. And basically just points to the offset after itself or something. I mean, a chunk file without any chunks is invalid. I call it invalid. You shouldn't have that because then you don't need chunks. I mean, it's not officially forbidden, but let's say for the multipack index, it makes no sense. For commitgraph, it makes no sense. So the two examples I have, they don't do that. So I assume that they don't just leave out the chunk index if the chunk size is 0. However, the chunk index here is not part of it. Like that minimal size computation, it doesn't even include the chunk index, the minimal size of the chunk index, which would be 0 chunks. And that's another 12 bytes here. So I'm thinking that this one here has a minimal index size that is actually too small. And maybe that's I don't know, maybe that would lead it to try to read files that are actually really too small, because this should be a bit, it must be larger, the minimal size, I'd say, to be valid. But anyway, that's just my opinion. And now it's GitOxide's opinion as well, because I do it like this. So I have the header lang here, which kind of shows why this is that magic number 12. It's these individual bytes and, you know, fields that you read. But also, where is it? The trailer. The trailer is the checksum that is at the end of the file. But there's also in between the header and the trailer, there's this chunk file index empty size. So how big is this chunk file index? If it's empty, and that's the empty size, it's the size of one entry. And this is how I get a different number for the smallest possible size of such a file. And I think that's the number I see more fitting. And doesn't matter. The Rust version is safe no matter what. And these tiny files that have nothing in it, I mean, makes no sense. But ideally, you don't crash when something weird is encountered and have decent error messages. So that's that. But yeah, would be interesting to throw in some malformed file to Git and see what it does. Now that you see the code, you can manufacture these, right? And you can let it run into spots where it shouldn't be. And there's one more that I found that is kind of weird, but anyway. So back to how this parses in comparison to commitgraph. And it uses this kind of style here. Maybe it takes a moment to understand what this does, but it overwrites, it rebinds data. So you see it's literally from the section of memory here, you take a part, you cut a piece off and take the two pieces separately. And this is what it does. And then you have a slice of size 4 here on the left. On the right side, you have all the rest of it. And this is how you cannot forget to do your offset calculation. You can't get it wrong that way, because you now, look, I shadow data, right? I can't access the original data anymore. I always access the truncated one. I always access the one that is past the thing I'm interested in. And this is, to my mind, a much more secure way of doing the parsing just for yourself, because that way you just don't get confused with some offset calculations or slicings, right? There is no slicing here. And that is, of course, bound checked. So if this is out of bound, this would panic. But we know it's probably not out of bound because we have this minimal size check before. So it shouldn't be. That's okay.
It's funny because also this way of doing it really only works nicely in Rust, right? Because you can actually shadow variables. If you didn't have that, you'd have to create new ones along the way, and it gets really confusing really quickly.
Yeah.
But with this, it's super easy to do, very elegant.
True. It's a huge benefit to be able to do that, huh? Not to be afraid of that. It's amazing. Think about the language designers who had to grow up with all the languages out there that don't like this, and then say, but what if we would allow it? What would the benefits be? Because it's all trade-offs. There's no good or bad. There's really just, okay, if you do this, then you get that, but you lose this. What's more important to you? So yeah. And if you do all the trade-offs right, you actually have this big thing that the whole that is actually better than the sum of its trade-offs, so to say, because it kind of falls together so nicely. And I think there's a big piece of why Rust is so nice to write, because I don't want to get into this mode again where I'm just like, Rust, oh, I love it so much. But it's just when I now think about the development experience, I've been sitting on this for like a couple of hours and I just plow through. It's just that. And this is showing you something. And it's not showing you that you're so great. No. It shows you that if you use Rust the way it wants to be used, it really helps you to just do the right thing. A couple of tests, the right tests, plus, a style that helps you. And Rust allows you to do all of these things easily. Really nice. Okay, so that's the way this is done here. Some checking. That's another way of doing it. These individual bytes, they also exist here, right? And it literally splits off 1 byte here. And then you have a slice of size 1. So that's kind of, then I reassign here again to get that 1 byte out. Yeah. You do this and you know that the optimizer will just take this away. The optimizer will, do what's right here and just make it work. This is all just abstractions here. I don't care. Of course, I would love to have a way to say, give me 1 byte only. I mean, there could be a method that does just that, right? Like, give me a byte, but there isn't, or I don't know it. Sometimes I say there are things not available that even though they are, like for each an iteration, right? But here I think it's not there. All right. Then, yeah, then it really just gets through its own header. And once this block ends, we have the information that we're interested in, version, hash kind, num chunks, num packs, and we have our original data back, because this data now refers to the overall file, and we just drop the previous truncation here. And that's also pretty nice. This is why this block exists in the first place. And it also is nice to kind of denote a certain section of things that you want to do there, like read the 12 bytes of header. So it makes sense to me. Yeah, and now for the chunking, like let's look at this for a second, just to see the overall structure and how it feels. Could probably be more condensed, but is it this? And now we compare that to this. So of course it's much more wordy, right? It's much more direct. We know that. And you can do that, but I do like this more. And this uses GiG-chunk file index from bytes. And all it does is you pass it the data, the original data and the header length or the offset to the table of contents or the chunk index, and then the amount of chunks that you expect. Because usually that's what you are supposed to put into your own file. I mean, that's the convention. So you don't just parse chunks to the next sentinel value like you could, but instead you parse as many chunks as you think there should be, kind of as an additional safeguard, I guess, against corruption. And then what this API allows you to do once you have the chunks, all you say is give me data or the offset by the kind of chunk. So I renamed this. I don't know if it's good or not. I mean, I call it kind because it really is not an ID. I mean, it kind of is an ID, but it's more like a kind of chunk that we store. It's not really, I mean, to me, it's not an identifier. Maybe, you see, I'm not really sure how to call it here myself, because that was before I wrote that git chunk, I think. So this also called itself ID here. So what we are able to do is we extract from this chunk offset information, we find the chunk of the given kind. Yeah, I actually liked ID more. Interesting. So maybe that's another renaming session here. So I really call this data by ID and just stick to what Git does there instead of doing it in a more rusty way, because Rust usually uses kind as a name. But anyway, it's still version 0.2, the Git chunk, so still some breaking changes that I can do. Anyway, it looks up the chunk offset in that data and then gives you the respective chunk. If it finds it, otherwise you can just abort with an error. And this is what you can do with these mandatory chunks, because these are always required. And definitely that. So, and then as a last step, what this always does is it just, extracts from that slice of data what it wants. This usually is a separate parsing step, or it validates it like here. So that's the pattern that is employed here, and probably, and also here, sometimes I don't get my names consistent because it's actually the same. it's actually index names. You might say, why is this peg names? Well, in Git, it says it's peg names, right? So these IDs, they're called pnum. So that's the name of the ID in ASCII. However, in practice, it's index names that are stored. So it stores peg-hash.idx and not .peg. Probably because it's a bit shorter, right? But this makes it, to me, okay, it's index names, not peg names. And then the next person coming around wanting to use these as peg names, then you're probably surprised that it's a .idx file. So I'm kind of renaming this here. Let's just call it index names. Index file names, actually. It's okay. Let's keep it a bit shorter. Okay. Yeah. So basically 2 lines you have here. And probably if you want, you can condense this into 1 line, but I didn't want to go too crazy with error types and with this. Rather, just make it like that and it's probably fine, you know. In Git itself, interestingly, it looks like that. So here Git parses all the basic header, and then it reads the table of contents. And this table of contents, that's the chunk file index. Oh, sorry, you were muted.
No, I didn't say anything.
Okay. Chunk file index. Okay, this is how Git does it. And with this index, you then have, you see the pattern repeat a little, like get something out of that index or fail. This is the C way of doing that. And they even have some callback mechanism, so they can pair chunks and read chunks, and the read chunks calls a function. Here it is a function that does a certain thing. So even in C, you have this, you know, passing function pointers around and being a bit more dynamic about stuff. Whereas I'm not doing that. I'm really just dealing with data. I was thinking about doing it, to be honest, but then I thought, yeah, why? It's, you know, you can just map things. You can basically use the typical combinators of options and results to do exactly the same thing. So why make a special thing out of that? But I do have 2 versions of it, data by kind and option offset by kind, so that you get the data for use more easily. Like in this case, when you parse the index names. So there's this chunk that is a bunch of file names, and here's where the parsing happens. Yeah. It's kind of funny because, you know, when you do this, you notice sometimes that things seem to be missing or certain parts are not checked. For instance, when you get a chunk of a certain size, you would probably want to consume the entire chunk. So if you parse it, you don't want anything left, because that's garbage bytes. Then you shouldn't have garbage bytes in a chunk, I thought. So I had this check here, if chunk is empty. So you see, I do the same thing. I use the slice here as cursor, so it's mutable. And I keep assigning to that slice after parsing. So I just offset it to the next thing that I want to parse. So after that, it's supposed to be empty. But if you do some error handling here, you see that actually in my sample file, it's already not empty at the end, even though I've parsed X amounts of pegs. So in my index, there is the amount of pegs that are supposed to be contained in that index. So I know how often I should repeat this parsing step. But in theory, the parsing step is unique enough to allow you to just parse until there's nothing more to parse. You can just exhaust the chunk. It should be possible based on that format description, but it's not, because Git somehow puts additional null bytes at the end of the chunk. So there's 2 extra nulls here that are simply not supposed to be there. And it's probably related to Git writing the chunk in a way that writes too many nulls for some reason. And there's no excuse for that. It's just garbage bytes. And you just gotta ignore the garbage at the end. Git-oxide will not write these garbage bytes. That's for sure. And that you know, that's the kind of stuff you think, yeah, Git is still Git. It's hard. Like this whole, it's not easy. If you do it in C particularly, I think. What else can you say? But in C, this parsing looks like this here. So it's kind of interesting because these file formats, they're always tailored to standard functions in C that you can use to find strings, you know, because strings have this null termination by default in C, null terminated strings. And yeah, you keep, it's not that easy in Rust, let's say, even though it's still very doable, but in C it's kind of lending itself to that. Yeah. Okay. So that's the style. That's the style employed here. Oops, I jumped. And then you do this for a couple of chunks. Some error handling here. To the end, the chunk index here has one more capability. It just gives you the highest offset that it knows. It's the end of the last chunk essentially, and they are always sorted from in ascending order. So left to right, they always increase. So you know the last chunk, and there's at least one, at least in my implementation, there must be one, otherwise you wouldn't be here. It's an error for me to have empty chunk indices. You can easily get the highest offset. And this function or this method here just exists so that this assertion here can be tucked away somewhere, because otherwise you would have to do that all the time. And yeah, with that checksum, with that offset, you get to the end of the file essentially, where there should only be a checksum over all of what came before. That's a typical Git thing as well, that their files are checksum protected. So the hash is used. Okay. Yeah, and that's already it. That's the parsing of multi-pack index. So it's not too hard at all. Look, it's just a couple of lines. And I'd say thanks to the chunk format, that becomes relatively easy and straightforward, because you now deal on a chunk per chunk basis. And I like that. I like the organization that comes from that. I like to create all these little modules here that really don't have much going on, but maybe their own, you know, way of validating or creating something from that slice. So you see here that path parsing, it gets the slice and it returns a vector of path that have been successfully passed or some specific error. And that's, you know, just repeating in these little modules. So one might say over-engineered. I mean, literally, right? It's kind of all these modules. But then again, it's so cheap and so easy to do, and it's just in one file. It's not that this is one file per module or something. No. It's just, you know, it reads nice chunk index names from slice. It, you know, kind of comes together.
Helps you to stay organized, helps you to make the API really nice. It just makes sense. It's seems easy to use as well. I like it too.
Yeah, I mean, this is the organization that multi-pack index chooses. The only thing that, only this chunk thing is what comes from Git chunk, essentially, this index right now. Maybe it's worth it to just also take a look at how the index parsing works. If IntelliJ ever catches up with the IntelliSense here, because that's not actually so many errors. Apparently it does not catch up. Okay, fine. Then we live with that. Or I broke something and didn't notice, but yeah, let's not compile now. It's fine. It's gonna be fine. Or is it? Chunk. It is indeed fine. Okay. Just IntelliJ. So yeah, so we know the amount of chunks in advance, and most of the code is really concerned with error handling here. So there's a ton of possible errors. Most of them I stole from Git, because Git usually does a lot of error checking. That's good. And mostly implemented it the same way that Git is implementing it, so nothing special there. So the num chunks is really something fundamental, so that you don't actually look for that sentinel value here. And yeah, I think there's nothing special, because ultimately one of these table of contents entries, it's really just 12 bytes. It's two things, the kind and the offset. And then you just, parse these and do some error handling. Like duplicates are not allowed. There can only be one chunk of a kind per index. And then it uses this cursor padding again to kind of skip to the next entry by advancing by the entry size. And that's how it gets the next offset that it also wants, which could be the sentinel. So that's the good thing, that we kind of checked the total size here already. So we know it's going to be big enough to do that kind of thing, to skip ahead to the one past or to the next index or entry. And then it just stores this information and returns a little abstraction on top, the index itself, so that you can then have a little bit of convenience, as we have seen before. And that's the chunk file format. And I think
Simple enough.
Yeah, it's already, that's it for the reading part. It looks like it. And next up, of course, is to make it work with the commit graph and bring that a little bit on par, even though I don't want to go overboard with that. I don't want to refactor this crazily. I really just want to throw the Git chunk in here where it matters and leave everything else exactly as is, because that should combine nicely. It's just a different style of doing this parsing, so why not? So it's basically replacing this part here with the Git chunk crate, and that should be working fine then. Adding a little bit more test coverage. Fun thing, here you also see that there's other kind of chunks that seem to be having some extra data here that you don't know how to deal with, because maybe it's not supposed to be there, maybe it's just buggy writing, don't know. So yeah, I still don't know what to do with this. Let's see, maybe one day we figure that out. Yeah, something interesting here that I think this code, and then I think that's also the end of this particular session. Something interesting here is the use of whenever there's some subtraction happening, you do it in a safe way, like doing saturating subtractions and checked subtractions, maybe even, or checked additions or checked conversions. So whenever there's anything that can overflow or underflow, then you are able to deal with that instead of just silently wrapping or overflowing or something like that. And that's really well done here. So you should always be kind of aware of your types. And whenever you do any kind of math operation on integers, in release mode, it will overflow. Can it possibly overflow? Because you're reading files, right? And files can contain a lot of stuff that is supposed to trip you up. And I say in Rust it's safe, but it can still, people can still put stuff there that makes you fail to load something, and then you can't read the repository and so on. And maybe that's avoidable by doing these kind of checks properly, and just doing the right thing.
So the difference here between saturating and checked is one fails and the other one kind of just sticks to the minimum or maximum value?
Yes, that's true. Saturating add, saturating sub just has the boundary at the min and max. And checked returns an option. So you then have to see if it really worked or not. And there's also wrapping add and wrapping sub, just to have the kind of normal behavior that you get when you do plus and minus, which I also use when I just expect it to wrap. And when you write this, like when I still remember when I worked on the new object database, they wanted to, there's a generation counter. Yeah, maybe even that. A generation counter, and I was about to write wrapping add. And then I thought, really? What happens if you wrap this? And then I realized, but if you wrap it, the logic is actually not working correctly anymore, because the logic does assume that it never wraps, because it's important for one thing to be larger than another if it's newer. Like more recent generations should be higher, right? And if you wrap, that's not the case always. So your invariant is broken if you would do that. And this is when I realized, let's not do that. Instead, let's just increase this from U8. It was a U8 before to U32. And now you see I'm reckless. Now I say, okay, if it wraps, then it's okay. Even though it technically still isn't okay. So looking at this, you should probably always think of what should happen here. And in a way, do you want to abort? What can happen if the logic fails there? And the answer is, it will not find an object. So if this wraps around and the logic does the wrong thing, it will find an object that otherwise it would find, or it kind of trips up that logic a little bit. But this probably means that it failed somewhere because an object could not be found. But also it fails after a long, long time. Now you have more than 4 billion possible generations, and it really doesn't change the generation often. Like it really keeps these very stable because that's important to the whole system. But just saying, let it run for a million years and you might get this rare bug, which was created because I did not think about that and just did the plus here, right? But it's okay. But it's useful to think about it. That's the point, right? Like probably you never want to write this, but always find what you want and then spell it out just to learn that it's probably the wrong thing. Because what can you do? This should always be incrementing. And otherwise maybe you panic right away. That's probably the best. Just stop it right there and say, I don't care if an object couldn't be found. Probably it's just fine. Just don't go there. Just abort. Fine. That's better. And usually that's the better choice to make. But I didn't dare to panic here. I just didn't. I guess this is also why I just write this and say it's okay. Nobody will notice this. I won't remember this very soon, so it's fine. It's not there. Yeah, but that's also Rust for you. It kind of forces you to think so carefully about every little thing, and it just makes for better software in the end. Yes. Okay, but that shall be it for today's session. Hope it's not too boring and you learned something about Git file formats.
Absolutely. Always interesting to see, specifically these different ways of handling this. I probably would have gone in a completely different direction as well. But you always learn something new. So thank you very much.
And thanks for getting through it. And I hope to see you for another episode next time with maybe more stats programming. And